Hi, this is John with Page Tutoring, and today we're going to be covering the Eduqas Foundation Mathematics paper from summer 2023. And this paper is Calculator Allowed. So let's crack right in. As always, when starting these papers, the first thing you will look at is the front page. It's full of very useful information. So say go to the additional material section, which is here. It'll tell you what we've got. So we've got a formula sheet. You're allowed a calculator in this exam and use it when you need to use it. And you might need a ruler, protractor, and a pair of compasses. You can also see here that this exam, as always, is out of 120 marks. Usually to get a grade 5 on a foundation paper, you need about half of them marks. So you're in for about 60 marks. Above that 5, the grade is capped because this is foundation. 5 is the highest that you can get. So going to the next page and looking at what formulas you have available to you. The first top ones, they're all area formulas. So for example, surface area of a sphere. So if in a question you are asked something relating to these areas, always remember you can double check your formula sheet and see if it has been given to you here. Though a lot of questions these days will just give you the formula as part of the question. And at the bottom you've got these kinematics, so you've got like velocity, direction, any question like that, you can use these equations. Question 1. The table shows the menu at a cafe. You've got a nice menu with main items, drinks and snacks. This paper came out in 2023 and these prices look fantastic by 2025 standards. So part A, Lucy buys a cereal bar, a coffee, a salad and a piece of fruit. Write down the price for these items in order of cost. Start with the cheapest. Okay, so let's start labeling the things on the menu starting with the cheapest. So let's see, if we look at cereal bar, so I'll get my laser. Cereal bar's 86p. So I'm going to write that down here because it's giving you a bit of room to write. So we're going to write all the prices down first. So 68p. And then a coffee is £1.85. A salad is £4.23. Very specific price. And then a piece of fruit over here is 60p. So now we've got all our prices in one place. It makes it easier to do this. So we can see 60p is the cheapest. Next up is 86p, and as you go in, feel free to cross them out. Next up is the £1.85 coffee. And then it's our £4.23 salad. Part B. The cafe offers a meal deal. Woo! Buy any main item with a drink and a snack for £5. Okay, so Jason buys a sandwich. Later he buys a tea and a packet of crisps. So he doesn't take advantage of this meal deal. He buys a sandwich and then he changes his mind, buys some tea and a packet of crisps. How much less would he have paid if he had bought these 3 items using the meal deal? Well, starting off, how much did he pay in the first place before the meal deal? Let's have a look. So we go up to our menu. So what did he get? He got a sandwich, that's £3.49. £3.49. And then he got a tea, which is £1.20. And he also got a packet of crisp. Classic combination. So a packet of crisp is £1. I thought this was a good menu. £1 isn't that great actually for a packet of crisp. £1. Okay, so let's add that up. This is a calculator paper, so feel free to just go straight to your calculator and start plugging things in. So £3.49 plus £1.20 plus £1. It's come out in fraction form, and you should know how to change the format on your calculator. So on this calculator, it's just this button here. So that's £5.69. So compared to that £5, we can write it's would have been £69p cheaper. We could have done the calculation, but luckily money makes it quite easy to figure out. That's 69p cheaper. Part C. On Monday, Emma buys 8 soft drinks. What's the total cost for this? Okay, well, it gives us random information we don't care about on Monday. Why do we care about the Monday? So Emma goes in, she buys 8 soft drinks. She might be buying it for her colleagues, who knows? It's going to be 8 times the cost of a soft drink. So if we go up, how much is a soft drink? On the menu, that's 95p. Once again, you don't have to do it in your head. Don't use your brain more than you have to. Save it for the hard questions. We're just going to plug that in. 8 times, and it's 95p, but in pounds, because we want to convert this to pounds straight away, it's 0.95. We want to convert that to pounds straight away, because if I click the equals there, change the format, that would have come out as 760 pence. But if we convert it to pounds straight away, £7.60 is a lot easier to think about in terms of money. So we were going to write that down. £7.60. On Tuesday, Emma only buys coffees. She spends £12.95. So that's a lot on coffees. I think Emma may be being sent for the office to get everybody a drink. So now let's have a look. In total, she spends this much money: £12.95, and that's equal to the cost of a coffee. So where's our coffee cost? So that's £1.85. Times an unknown factor, an unknown number, so n. Now you can think of this in terms of algebra, or you could just think of this in terms of your basic arithmetics with just numbers. But to get what this value of n is, how many coffees she bought, you just divide the final number by the cost of a coffee. Once again, we're just going to plug that into our calculator. £12.95 divided by £1.85. And that comes out with exactly 7. So the answer is 7. She's bought 7, and you can write next to it coffees. So the examiner knows that you mean 7 lots of coffee. Question 2. Straight away we can see lots of graphics, and I can see the words symmetry written multiple times. So let's have a read. Part A. Complete the pattern below so that AB, okay, so where's AB? Here's point A and here's point B. So that means that AB is this line here in black, which is a little hard to see in our grid, but we'll put it in red there. AB is a line of symmetry. Okay, well, what does line of symmetry mean? It means that on either side of this line, that pattern would look exactly the same. It says shade the smallest possible number of squares. So we're not taking away squares, we're adding squares. So what I'm going to do, by row, so say this is a row, this is a row, I'm just going to go up and check that they're symmetrical. So bottom row, there's nothing on them yet. The second row, each of them have a gap, and then they have a cube when looking relative to the line of symmetry, so that's fine. The third row, that's also symmetrical. Now the fourth row, if we look here, there's 2 on the left and only 1 on the right. So we're going to make that row symmetrical by shading in this cube. So now that row is fine. And then the fifth row, we've got a cube on this left hand side, but we don't have anything on this right hand side. So we're going to fill in that cube there. And now that row is symmetrical. Tick. On the sixth row, we've only got 1 cube on the left, 2 cubes on the right, so we're going to make 2 cubes on the left now. And then looking at number 7, number 8, we could straight away see there's nothing there, that's already done. So number 7, we can see there's a cube on the right, but nothing on the left. So we're going to shade in the corresponding cube. And now we look at our shape. I'll shade that in a bit more so it looks more symmetrical. But we can see, yeah, that's symmetrical now. We're happy, we've got 2 marks. Part B. Circle the shape below that has rotational symmetry of the order of 4. Now what does that order of 4 mean? It means if you rotate it 90 degrees, 90 degrees, 90 degrees, it's going to be exactly the same shape. Or another way to think about it is it has 4 lines of symmetry. So this top shape that we've just done, that has 1 line of symmetry, so just 1 line through it. But now we're looking for shapes that could have 4 lines through it. So let's start discounting some. So if I get my red pen, I've got my line to go through. So I can see there's a line of symmetry here. You could have a line of symmetry here. So that's 2. But you couldn't go down the middle, because then if you reflected, one side would have black, the other side would have white. This only has 2. And let's just keep doing each shape. So I can see that though this looks quite symmetrical, and I'll just zoom in so you can see a little bit here. These are circles, top and bottom. Circle, circle, and then the left and the right, they're cubes. So I could have a line of symmetry here, and I could have a line of symmetry here, but I couldn't have, for example, a line of symmetry going diagonally here. So I'll show that with the pen here. Because then I would have on one side of the reflection a circle, and the other side of the reflection I would have a cube. So once again, that's only 2. Moving along, we've got 2 circles here, 2 circles here. I could put a line through the middle here. It's not quite in the middle, but it's close enough. I could put a line through the middle this way, so we've got 2 so far. But I couldn't, so I'm going to draw this in now to make it a little easier to see. I couldn't have one here, for example, because if you look on now the left-hand side, you've got a circle, and then the right-hand side of this blue line, you've got nothing. I'm going to get rid of that blue line, and I'm going to call that 2. Now let's have a look at this shape. So if I have a point here, and I rotated this 90 degrees, what would this shape look like? Well, imagine this hemisphere here, and it'd rotate 90 degrees to then lie exactly here. Well, then where would the other hemispheres lie? So if that lies there, then the next one would follow and follow and follow, and voila, the shape would look exactly the same. So rotating this shape 90 degrees means it'd look the same. So this shape has an order of 4 rotational symmetry. So we're going to now circle this shape. We don't have to check the last one. Part C. The diagram below shows a triangular prism. It says the diagram's not to scale, so that gives you the nice little hint. Do not use your ruler, or do not use any other mathematical tools like compasses or protractors. So it says how many edges and vertices does the triangular prism have? And you have your nice diagram so you can count them up, but it's just knowing what edges and vertices means. So edges, self-explanatory. An edge would be, for example, straight along here, so that's an edge. This is an edge. This is an edge, and you'll see that I'm just outlining the actual net of the prism. Not very straight, but there you go. So it's all of these long straight lines. So let's count them up. We've got 1, 2, 3 on that end, 1, 2, 3 on the other end, and then for the middle we've got 1, 2, 3. So that gives us 9 edges in total. So where are the vertices? Well, vertices are where lines meet. So I'm going to do this in green. So where are all these lines meeting? Well, you've got a point where loads are meeting there, a point there, a point there. You've got a point here, here, and here. Okay, well, how many points have I got there? That's just 6. And that's it. That's all the marks for your answer. So you'd get 1 mark if you could only guess, okay, I think edges are the lines, maybe. And you get the other mark for knowing what that word vertices means. It's just where all the lines meet. Part D. So I'll just zoom in there so you can see a little better. Draw 1 line to connect each of the following mathematical names to the correct shapes. You will not need to use every shape. One has been completed for you. Okay, so some of these, if you don't know them, you might be able to get them just by guessing. But let's have a look what we've got. We've got rectangle, which is already labelled for us very nicely there. Rhombus, trapezium, kite, and hexagon. Well, let's start with the more obvious ones. So kite, that looks like a kite that you'd fly in the sky. So a classic kite looks like this. You might just know that off the top of your head. You might be able to guess it if you're not sure. And the kite shape is that diamond there. Okay, well, have we got any diamond shapes? Here we go. So we're going to label that straight away on here, a kite. So now hexagon. Hexagon, a lot of people know the hex in that means 6 sides. A hexagon shape with 6 sides. So there's 2 shapes here that look like your classics, so say hexagon, septagon, decagon. They keep going up and they keep having a certain number of sides. So the gon part of that may look familiar. If you're not sure which one it is, you're going to know it's either this one that has 5, this one that has 6. But off the top of the heads, we know that hexagon, hex means 6. So it's that one. So now we've just got 2 that we don't know. So let's do trapezium. You might know trapezium from the trapezium rule. So how to find the area of a trapezium. And you may remember that it's adding the top line and the bottom line. So you're like, okay, well, it's a shape that has a line, 2 lines that are parallel. It's going to look something like this. Ooh, trapezium. Something like this. You may even remember that the top line and bottom line are different lengths. Okay, well, I'm looking for the shapes that have parallel lines that are horizontal. So it could be this one, could be this one, and it could be this one. By process of elimination. The most important part there is then to go, okay, I'm going back into my memory about the trapezium rule. What else did I know about a trapezium? Well, you should know that the other 2 sides are not parallel. So that tells you that the trapezium is this one down here. So now this is getting a little messy, so I'm just going to clear up over here. But the next one is a rhombus. And because you've got some already with lines, so you could even circle them to make it a little easier to see which ones aren't taken. So this one's taken, this one's taken, and this one's taken. Rhombus does not have a gon at the end, and you know that this is some sort of gon, so you know it's not that. This rectangle's already taken. We just scroll up, so it's either going to be the top one or the bottom one. Now, what's the top one? It's got all these little notches, and the bottom one also has notches, but they're lines. So we zoom in a bit, and you go back into your memory. When they're arrows like this, that means that these lines are parallel. And you can see there's 2 sets of parallel lines here, 2 sets of parallel lines here. And that should give you the hint that this shape up here is a parallelogram, which I'm going to spell terribly, but thankfully, math, you do not need to spell it correct. Parallelogram. Something along them lines. So lots of parallel lines is a parallelogram. So if I go down now, zoom out, even if I didn't know what a rhombus was, and even if I didn't know the definition of rhombus is a shape where all the sides are the same, but the lines are not at right angles, I could have just found that through process of elimination. So with these, yes, you can just guess. Yes, you might have a chance of getting the correct mark because you have 2 marks to get there. But if you just use process of elimination when you're not sure, then you can get yourself some nice, easy marks. Question 3, part A. Peter uses numbers and a symbol to correctly write 1/7 is greater than 1/8. And it says circle what Peter has written. Okay, well, starting off with the greater than, you should be thinking back, and in the lesson, a classic way to teach greater than, less than, and how I still remember it myself, is the hungry crocodile. The hungry crocodile wants to eat the bigger number. And you can see down here that you've got lots of little hungry crocodiles. Cool. But some of these hungry crocodiles have a little line underneath. And that little line underneath is to make it look very similar to an equal sign. And that's because when it has a little line underneath, so for example, this one on the left is eating the bigger number, saying 1/8, that means 1/8 is greater than or equal to. So we know it's not these ones because it's not greater than and equal to, it's just greater than. And then 1/7, it has the word 7 in it, so that's 1/7. 1/8, so that's 1/8. And where's it written like this? We can see that right here. Part B. A large jar contains 8,571 jelly beans. Oh, I bet they're all sticky and stuck together. Ooh, a bad way to store jelly beans. 2,857 of the jelly beans in the jar are blue. Use one of the 5 options shown below to complete the sentence. So what's the sentence say? So something of the jelly beans in the jar are blue. And you've got 1/5, 1/4, 1/3, 1/2, 2/3. So that's all in words. And hopefully from previous videos you're getting the gist that I'm not a fan of words, being someone who is dyslexic. So any chance I get, I'm going to convert this into just numbers and just maths. So 1/5, that's 1/5. 1/4, a quarter of something, that's 1/4. 1/3, 1/3. 1/2, 1/2. And 2/3, so that's 2/3. Okay, so we want to know what fraction of the jelly beans are blue. Well, you've been told that it's 2,857 of the jelly beans are blue. And that's out of, so that means over, 8,571. Now, always remember, calculator question, you do not now have to simplify this. Straight away, you should be rushing and reaching for your calculator to just plug in the numbers. It's 2,857. And you could write this as a fraction. Some of your calculators have options for fractions, but you should know about fractions, that writing that this over this is the same as writing the top number, so the numerator, divided by the denominator. So 8,571. And if I click equals on my calculator now, the calculator itself will give you the simplest version of that fraction. It's giving you 1/3. You can see that that's the option there. It says complete the sentence. We've circled it just in case we've got a really mean examiner. We're going to make sure that line's not got anything else on it, and we're going to write in words 1. Part C. 3 of the factors of 18 have a sum of 17. So sum, that means when you add up the numbers. So it's going to be 3 numbers added up. You don't know what they are. And they've given you a nice diagram, or well, they've put places actually to fill in the boxes, but you could even write down here that add there, that equals to 17. Write these factors below. We'll start 1. What are the factors of 18? You've got 1 and 18, 2, 9, 3 and 6. Okay, so we've got all 6 of our factors. Now we want them to add to 17. Well, 18 of course is way too big, so we can cross that out straight away. So we could have 6, 9 and 2. Now I'm doing that by observation and sort of guessing what it's going to be, because I'm like, well, I want it to be kind of big but not too big. You could just go through each one of these and just try them all out if your brain doesn't work like that. So you could go, okay, well, I'm going to do 1 plus 18 plus something, blah, blah, blah. Oh, that's too big, not that one. 1 plus 2 plus 9 equals too small, not that one, until you find the right one. But I know that it's 2, 9, and 6. Question 4. Reese owns a bakery. Good for Reese. Entrepreneur. He recorded how many cupcakes he sold each day. The results for the first 4 days are displayed in the pictogram below. Below is a key. You have a diamond that's split into 4 segments. And it says that represents 12 cupcakes. So straight away, before we even read the question, if that diamond can be split into 4 parts and that represents 12 cupcakes, then that means that one part must represent 12 over 4. So that's 3 cupcakes. So we'll go down, selling different amounts each day. So let's first figure out what it actually wants us to find. Part A. Reese sold 42 cupcakes on Friday. So it says complete the pictogram for Friday. Well, at the moment there's nothing at all in Fridays, so we can just start drawing straight away. So we're just going to keep adding these diamonds until we get to 42. So we're going to do a full diamond, that's 12, another full diamond, that's 24, another full diamond, 36, but then if we did another full diamond again, that would give us 48. That's too high, that's 6 too high. But we've already worked out when we were reading the key, because we knew that this was going to be useful, that each small bit represents 3. So at the moment we're at 36 and we want to get 6 more to get to 42. So that's just 2 quarters, so half of that diamond. Part II. How many cupcakes did Reese sell in total from Monday to Friday? So now we're just going to go through each one of these days and count how many there is. So the first one has 3 diamonds, so that's 36. And remember, if you can't do these in your head, you're not good at the arithmetic. This is a calculator question. You can just plug it into your calculator. So the second one, we've got 12, and then we've got 3 quarters, 3 for 1 quarter, 6, 2 quarters, and 9 for 3 quarters. That's 9 plus 12, so that's 21. The next one, 12, 24, 36, 4. The next one again, so that's 24 plus 6, so that's 30. And we've already been told that Friday is 42. They're being nice. So now it's saying how many did he sell in total? So we're just going to add up our numbers. So 42 plus 30 plus 48 plus 21 plus 36. We don't need to do that in our heads because we have a calculator, so we're just going to plug that in. So in total we have 177. Part B. On Saturday, Reese sold 17 cupcakes. Explain why the key used for the pictogram is not suitable to show this. So let's think about 17 and let's think about the factors of 17. So we could do 17, we could do 1 and 17, and then that's where we stop because 17 is a prime number. And what I was trying to find there is if a factor of 17 would have been 3, because our key and our little shapes, the smallest number that we can show is 3. So you could say that 17 is not a multiple of 3. Question 5. Straight away we can see our friend the number machine. This should get your brain thinking about algebra, but you can do this all arithmetically if you are not a fan of algebra. So that means just using numbers. So it says the diagram below shows, as I just said, the number machine. You've got your input, you multiply whatever your input is by 6, and then you're going to add 2.3, and then you have your output. So when it says input 8, what's the output? So it's got a bit of writing space here. You could just plug it into your calculator, but sometimes it's good to just write it out to make sure you don't make mistakes. So you've got 8, you're going to times by 6, and we know off the top of our head it's 48. If you didn't know that, then you can always just use your calculator. At this stage here, so then we're going to add 2.3. So that gets us to 50.3. Next it says when the output is 34.7, what was the input? So we're just going to use this number machine working backwards. So we're going to start here, 34.7. And working backwards means at each stage, if you're asked to add something, instead we're going to take away. If you're asked to multiply, you're going to divide. And you're going to do it in the direction of this red arrow here. So starting with your output, first we're going to take away 2.3. So that gives us, always use your calculator if you don't know, so that gives us 32.4. So next, it says multiplied by 6, we're going to divide 32.4 by 6. Now I can't do that in my head, so I'm going to get the calculator out and put 32.4 divided by 6. Change the format, so I've got 5.4. I'm going to circle it so the examiner knows that that's the answer that I'm putting. Part B. The diagram shows some boxes and some balls on balance scales. Now you should know about balance scales, like this type of scale that you're seeing here, that whatever's on one side is equal to whatever's on the other. So I'm going to put some equals here and some equals here. It says all the boxes have the same mass. So mass, you should have bells ringing in your head. Mass also means like weight. All the balls have the same mass. So it's the same for the balls. These two balls are the same weight, and all of them squares, the cubes or boxes, are the same weight. So it says calculate the mass of each box and the mass of each ball. Although it may not initially look like it, because you've got like a picture here, what this question is leading you to do is actually convert this to algebra. And we could even, rather than using letters, if you're not a fan of algebra, just leave it as the shapes. So we know that 6.5 kilograms is equal to, how many cubes have we got? 1, 2, 3, 4, 5. So 5 lots of cubes. So starting with this one, well, what would 1 cube be worth then? Well, that would just be 6.5 kilograms divided by 5. 6.5 is the weight of 5 cubes. We want to know the weight of 1. We're dividing it by 5. So out comes the calculator. So we got 1.3. So now, looking at the other, because we're trying to find the mass of each ball, we can write that out again, the same way we did the first. So we've got 5.5 kilograms equals, we've got 1 cube, but you already know the weight of that cube, that's 1.3. So you can just write it as 1.3 kilograms. And then plus 2 times the circles. I'm going to make that very circular, and I'm going to shade it in so you know it's a circle and not an O. Okay, well, what do I do first? So I'm running out of room here, so I'm going to go down. Well, first, I want to get it so I only have these circles on one side. I want to take away the weight of this cube. So I'm going to do 5.5 kilograms minus 1.3 kilograms. So that would be 4.2 kilograms, which I did in my head, but but you can do with a calculator. Okay, so that's equal to 2 circles. So now, same as we did for the first one, we want to know the weight of just one circle. Oh, that was a very wonky circle. How do we do that? We just divide this 4.2 kilograms by 2. So that will give us 2.1 kilograms. So now they've given you boxes to write your answers in, so make sure to use them. So for each of these, so the ball is 2.1 and then your box was 1.3. Question 6. Philip has 250 coins in his money box. So we've got a nice depiction of his money box. It's a classic pig-shaped place to put your coins. And it says 22% are £1 coins, 2 over 5 are 20p, and the rest are 10p coins. So it's got fractions in one bit, percentages in the other. Part A. How many of the £1 coins are there in Philip's money box? Okay, so we care about the 1 point coins at the moment, so we're just going to box that off. So how do you find, so it says 22% are £1 coins, so that's 22% of 250. So write that there. Of 250. So how do you find 22% of 250? Well, you could do it in 2 steps. You could do 250 divided by 100, because 250 is 100% of 250. So you could even write there, that's 100%. So to get 1%, you divide 250 by 100, so that's 2.5. You can always put that in your calculator. And then to get your 22%, you do 22 times 2.5. And I can't do that in my head, so I'm going to get the calculator. 22 times 2.5. So that is 55. Next, how many 20p coins are there in Philip's money box? Well, we've been given a fraction for the 20p coins, so we've got 2 over 5. And if you're trying to find 2 over 5 of 250, well, you just do the fraction times 250. And you can just plug that straight into your calculator. Now we're going to use the fraction sign, so 2 over 5 times 250. That gives us 100. If you weren't too sure how to plug that into your calculator or how to do this, you could always convert this into decimals if your brain works better like that. So 2 over 5, you could times the top and bottom by 2. So that would be equal to 4 over 10. 4 over 10, that's just 0.4. And then you could just do 0.4 times your 250, or you know that's 0.4, that's equal to 40%. Just however your brain works better. Do you prefer fractions, decimals, or percentages? It's very easy to switch between. So now it says, what is the total value of the coins in Philip's money box? Okay, well, we know how many £1 he's got. So we've got 55 times £1 plus how many 20p's have we got? We've got that 100 there. It's 100 times 20p, and plus the rest. Well, we've not worked out the rest yet. So at the moment we've counted, what is that? 155 of the 250 coins. So if we've already counted 155 and in total there's 250, that means that there's 95 coins remaining, because 95 plus 155, that equals 250. And it says the rest are 10p, so I can just write that in. So now we just need to put this in our calculator, but before we do that, leftmost monetary value is in pounds, but then the rest are in pence. So we want to convert one of them to the other. So I'm going to go for pence because it's nice and easy. So rather than 20p, I'm going to write 0.2 pounds. And rather than 10p, I'm going to write 0.1 pounds. And now it's just a case of plugging that into my calculator. So I can just write out exactly what I've written. Because of BIDNAS rules, it'll work in the correct order. So 55 times 1 plus 100 times 0.2 plus 95 times 0.1. So I get £84 and that's 50 pence. The calculator will write it as 0.5, but you know 0.5 of a pound, that's 50 pence. Question 7. Now we have a nice picture of a car there, and the first thing that we should be noting in our heads is it doesn't say anywhere that this drawing is not to scale. In fact, below that drawing of a car, it has a little box, so I'll just get my laser to point to it. It's a little box here that says scale. Each 1 centimetre represents half a metre. So this is a scale drawing of a car, and for every centimetre that's on this bit of paper, in real life, so like the full-size 3D car, it would be 1 metre long. And it says, Reem has made a scale model of her car. We can see that here. The diagram below shows the plain view of her model. Okay, so all of these words up here we can now ignore because we can just glimpse that from looking at our diagram. So if we go to part A, it says find the length of Reem's actual car. Well, we've got a scale drawing. It doesn't say it's not to scale, so that's leading us to use a ruler. So in my software, I'm just going to get up a ruler, drop that in. Now I found with my software, for some reason, the scaling is off. So if I put my ruler there, it's 7.5. But if I look in the actual mark scheme, and if you had a full A4 sized printed version of this exam, you should be measuring 9 centimeters. I can see that there, 9 centimeters. So say if you had printed the exam and to save on paper, you've printed it half the size, you've got A5 sheets, you would instead be measuring 4.5. But for now, we're going to assume this is full size A4 paper. We're going to assume that my ruler is the correct scaling. And when I measure it, it's going to say exactly as the mark scheme says, it's 9 centimeters long. We can even write on there, measured with ruler. Okay, so now we know how long the scale model is, but it says find the length of the actual car. Well, on this scale, it says for each centimetre, so we've got 9 lots of 1 centimetre, it represents half a metre. And if you find it easier to think like this, we can convert that fraction into decimals as 0.5 metres. Well, because we've got 9 lots of 1 centimetre, that means in real life we would have 9 lots, so 9 times that's 0.5 metres, which you might know off the top of your head, or you could put straight into your calculator, but that comes out to 4.5 metres long. Part B. The height of Reem's actual car is 1.7 centimetres. So this time we're working the opposite way around. We know that his car is 1.7 centimetres tall. So he's almost got a limousine. He's got a really long car, but it's 1.7 metres tall. Calculate the height of the model car. Okay, well, we'll look at our scale again. So for every half metre, it would represent 1 centimetre on his scale. So we want to know how many lots of that 0.5 metres is in the total height. So we're going to get the calculator out because I could not do that off the top of my head. And now we're going to type in 1.7 divided by 0.5. and we get 3.4. So there's 3.4 lots of that 1 centimetre. Well, 3.4 lots of 1 centimetre, that's just 3.4 centimetres. That's it. Question 8. First we see that there's lots of numbered cards. So this might be a probability question or something to do with range and mean. So let's start reading. It says Shahzad has 6 numbered cards. Part A, what is the median of the numbers on Shahzad's cards? Okay, there's 2 marks to get there. So first of all, what is the median? Well, the median is when you put all of these cards, all of these numbers in order from smallest to largest, so small to large, and then you pick the middle of them numbers. So you put middle. So let's just start putting these cards in order. So the smallest one is 13, then 15, and feel free to cross them off as you write just so you can keep track. It's 13, 15, 17, 21, 23, and 31. Okay, well they're all in order now. So which one's the middle? So we've count 3 from the left, and then 1, 2, 3 from the right. You actually end up with a number that's in the middle between 17 and 21. Well, what would that be? Well, we would do 21 plus 17 and divided by 2, which thankfully we don't need to do in our heads, but if this was a non-calculator paper, 21 plus 17, that's 38, divided by 2, and then we should know that that would be 19. So that is our median. So all we've done is put the numbers in order, found that the middle would be between 2 numbers, and we found what number is exactly between them 2 numbers. Part B. Liz says, I can pick 5 of Shahzad's cards that have a mean of 21. It says, which 5 cards must Liz pick for her statement to be correct? Now this is a little bit of a process of elimination. So first, keep in mind, what's the definition of your mean? How would you find your mean? Well, your mean would be equal to them 5 cards added up. So you could draw them as little boxes, 1, 2, 3, 4, 5. And then divided by the number of cards, so divided by 5. And the mean is 21. Okay, well you may be asking, I've got 5 unknowns. How am I meant to work out 5 unknowns? But what you can do now is go, okay, well then 5 unknowns, I've got my equation for a mean. And if you solve for them 5 unknowns, so if you get just these 5 unknowns on one side, no numbers like this divided by 5, then we can figure out what them 5 unknowns are meant to add up to. So if we do 21, so I'm just timesing each side here by 5, so times 5, all these unknowns divided by 5 times 5, this is 21. It's the same way you'd arrange algebra. So 21 times by 5 would equal my unknowns added together. Okay, so what do I get? Let's get out our calculator and plug in 21 times 5. So all of the numbers up added would be 105. Okay, well we now know more information. We don't need to just randomly guess the numbers, and we don't have any dividing. It's all the numbers added up would be 105. You may ask, okay, we've got 6 cards. How am I meant to do that? Is it just process of elimination? This is going to take me ages. No. What we're going to do is we're going to be a little bit clever with it, and we're actually going to add up all 6 of the cards and see what that equals, because the difference between our 105, that would be the value of 5 cards added up, and the value of all 6 cards added up will tell us the number or the card that would not be included in this list. So if you included that card, it'd be too high, it'd be above our 105. So let's just plug into our calculator all of these numbers. Now we were crossing these off before, hopefully you've not completely scribbled them out. If you're ever doing crossing or stuff like that, it's always good to use a pencil just in case you need to go back and have a look. So now we're getting up our calculator and just adding up all of the numbers. So 17 plus 31 plus 13 plus 23 plus 15 plus 21. And you could always scroll back through your calculator to check that you've put indeed, yeah, that's 6 numbers there. So that equals 120. 120, 105. We could take them away from each other and see what the difference is, and that would be 15. So if you had all 6 cards together, it'd equal 120, but we actually want it to be 15 lower than that. We want to take away one of the cards to make it 15 lower. And lo and behold, one of our cards is actually 15. So all of the remaining cards here must add to equal 105. So now we just need to copy that out below. Question 9. We can see a nice diagram. We've got some triangles. We've got an angle that we don't know here that's been marked as X. And we've got some what appear to be squares. And it says at the top, the diagram shows 3 identical squares. So we know that these are indeed squares. And it says calculate the size of angle X. Well, we can calculate angle X based on what we know about these different shapes. So what do we know about a square? Well, square, we know that in each one of these corners, it would be 90 degrees. That's what that little straight line square symbol means there. So we're going to put that, and oof, that was not very straight, but I'll write 90 degrees because it'll make it a little bit clearer. That is meant to be a little square in that corner. And we don't need to mark anything else because we don't care about these other angles. We're just finding this value here, and we're not going to do more work than we need to. So okay, we've got our squares, we've marked on our angles there. Well, what can we learn about this triangle? Well, if its sides are squares and they're identical squares, that means that each one of these sides is the same length. And what do we know about if a triangle has all the sides the same length? Well, that would just be, you could draw an arrow there, an equilateral triangle. So a triangle where all the sides are the same. And what you should know about an equilateral triangle is when all the sides are the same, each one of these angles is going to be the same. And I'm going to do it with 2 lines there to show that that's the same angle. Well, in total, how many degrees is in a triangle? Well, you should know triangle equal to 180 degrees. So if each one of them angles inside that triangle, there's 3 angles inside that triangle, add up to 180 degrees, that means each one of them angles, so I'm going to draw it on like that, must be equal to 180 degrees divided by 3, equally distributed between them 3 corners. So that would be 60 degrees. Okay, so we can mark our 60 on here. Okay, so we've got all of the angles surrounding that X. But now we want to find X. Well, what do we know when we've got all the angles around this point? So you could say angles around point or around a circle, point equals to 360. Well, now we can start writing that up. So we know that 360 degrees is equal to all them angles added up. So we've got 2 lots of 90 degrees. So we've got 90 degrees plus 90 degrees. That's from that square. And then we've got our triangle corner there, which is 60 degrees, plus our mystery angle X. Well, now it's just a simple algebra problem. So we can say 360 degrees equals, we'll add up these angles here. So you can put this in your calculator or do it in your head. So 90 plus 90, that's 180, plus your 60, that's 240 degrees, plus x. So something plus 240 degrees equals 360. So you could work it out like that as a word problem, or you could solve this algebra. So we're going to take 240 from each side. Take 240 from each side there. There we go. 360 minus 240, that's just 120, which you could have done in your calculator if you wanted, equal to x. That's it. You've solved it. So now we're just going to write this here, 120. And that is the end of question 9. Question 10. Before you even start reading, you can see there's a nice graph there, and it has a y-axis of kilometers, an x-axis of miles. So you can think, okay, that line is converting kilometers and miles. You can use that to convert between the two values. And it says the conversion graph. Look, before we even read the words, we already knew what it was. These graphs are really useful. The conversion graph below may be used to change between distance in miles and distance in kilometers. So if you couldn't glimpse that just looking at the graph, it physically tells you that there. Now it says use the graph to answer the following questions. Aaron and Jenny both went for a run. Maybe they're good friends, maybe they're training for a marathon. We don't know, and we don't care, frankly. We only care about the numbers. So it says Aaron ran 28 kilometers and Jenny ran 15 miles. Who ran the longer distance? Well, at the moment we can't really compare them very well because 28 kilometers, it's on a different scale to 15 miles. So what you're going to do is you're going to choose whichever you prefer, miles or kilometers, and whichever runner is running opposite to the unit you've chosen, we're going to convert it. So that's easier to show than to explain. Kilometers, metric unit, I like kilometers. So I'm going to say, okay, well, I know that Aaron ran 28 kilometers. That means for Jenny, I'm going to convert her 15 miles into kilometers. So what you can do is do a straight line up from your 15 miles until you hit your line. Okay. And then you're going to do a straight line across. So to draw these straight lines, make sure to use your ruler, make sure to use your pencil. I'm going to do a straight line across from there to my kilometer line. I have used quite a thick line, which is fine because usually there's a plus or minus a certain amount. There's a lenience for if your ruler moves or you read your reading a little bit different. So that lenience means you're going to get full marks even if your mark's a little bit different from everyone else's. So now we just need to read this graph. So it's 30 up here, it's 20 up here. Between there's 1, 2, 3, 4, 5, 6, 7, 8. So there's 10 notches, and our line comes to 1, 2, 3. So the fourth notch. So that's 24 kilometers. So they're both running a really far distance. Goodness me. So they're running further than a half marathon. So that's pretty far. So now we can just write that there. So she's ran about 24 kilometers. So we can say that Aaron's ran an extra 4 kilometers than Jenny. Now it says complete the following statement. You must show all your working out. And it says 36 miles is equal to something kilometers. Well, let's have a look. That's in miles. And if we go up to our graph, you'll see that the graph doesn't actually go up to 36 miles. We don't have that option. And we're like, ooh, oh no, what have we meant to do? But what you can do is think about line equations. And you might be going, oh God, this is going to get really complicated. No, it's okay. So you may recognize it written down like this, plus C. This is the standard format for the equation of a line. This C would be where the y-intercept is. But luckily, if we go to our graph, the y-intercept, so where that line crosses your y-axis, or in this case the kilometers axis, it's 0, which means we don't have that term. We can just cross that straight out. So then the next thing we need is, what is m? Well, m is our gradient. And how do we find the gradient? Well, normally you would take 2 points, and this is going to look a little bit complicated as I do it. You take 2 points, so a point here, a point here, and you're finding what this height here is. Just that's your y, this here, your x, and you're going to do, so we call it y, we'll call this 1.1, 0.2, we'll call this y1, y2, x1, x2, and you might be going, oh, there's so many different things here to remember. And then you would just do x2 minus y1 over x2 minus x1, and that would be your gradient. But you don't need to remember that, and you don't need to do any of that, because they've been very nice with you here. They've not given you a y-intercept. And when you don't have your y-intercept, that means essentially what you're going to do is have your first point here, that's just 0, 0. And then your other point, you could have where you've already measured, you've already done your work. And if you were to do, so the y value here minus the y value here, well, the y value here is just 0. The x value here is just 0. So actually, what you end up doing is you'll just do your y value over your x value. Or, in this case, kilometers at one point over miles. So what is this value? We've just worked it out for Jenny. You know for Jenny, so the x-axis is kilometers. You know for Jenny that it would be 24 kilometers over your value in miles, so 15 miles. And can't do that in your head, get your calculator out. Gonna get calculator there. And we're just going to put in, so clear that, and we're just going to put in 24 divided by 15. That gives us 1.6. And you could put in unit if you wanted to, you don't really need to. Okay, so you've got your gradient, so now you've got an equation here to find and work backwards from. So now you can put in, see y, that's kilometers. Been very nice with you here because it's the right way around. So to find the value in kilometers, you just need to times 1.6 times what they've given you in miles. So all I'm doing here is substituting into our equation. We know what our gradient is from over here. We know what our x value is, that's the miles, they've given it us there. And now we're just solving for that y, or that kilometers. So once again, we're just going to plug this straight into our calculator. Get rid of that, so 1.6 times 36. That gives us 57.6. Question 11, part A. So we can see we're going to be doing algebra now. So it says simplify, and then you've got your, it's not an equation, there's no equal sign. So this is just an expression. You've got your algebraic expression here. So when we're simplifying, we don't want brackets. Brackets aren't simple, so we're going to expand that out. So first you do your 4 times your x, so that gives us 4x. Then you do your 4 times the second term, so we're going to do 4 times 6, so that gives us 24. And then we're going to add 3x. But now we can see that's not the simplest term, because we've got an x over here and an x over here. So we're going to gather them together. I'm going to do 7x plus 24. Part B, we're going to solve for this f over 3 equals 5.1. Well, when you're solving, that means you're going to find that value of f. We want f on one side on its own. To do that, we need to get rid of that divide by 3. So we're going to times both sides by 3. She'll end up with f equals 5.1 times 3. You can put that into your calculator, but I can do that in my head. So that's just 15.3. Part C says find the value of x when w equals 3 and y equals 24. So this is a substitution question. So luckily you don't need to rearrange this equation. You've already got x on one side here. So we're just going to slot our numbers into the formula to get our value of x. So we've got w as 3, bracket, our y is 24, plus 2 over 8. You could plug this straight into your calculator if you wanted to, or you could use BidMass rules. So that just means the first thing you would do is add the things in your bracket. So you'll have 3 bracket 26 over 8. Indices, we don't have any powers there. We don't have any squares or cubes. Divide and multiply. Well, we're going to do the multiplication on the top first, just for simplicity. So you could do 3 times 26 and then divided by 8. At this point, I'm going to get my calculator because I can't do that in my head. So I'm just going to do 3 times 26. It's the first part of the calculation. So that's 78. And then I'm just going to divide now by 78. I could have done that all in one go, typing in my calculator. You have brackets, you have fractions, but I know I can do it in 2 parts. I can do 3 times 26 and then divide it by, not divide it by 78, divide it by 8. So I will get 9.75. But you can also leave that as a fraction if you wanted to. So if you put 39 over 4, you would still get full marks. If you put 9 3/4 instead, you'd still get full marks. So that's 9.75. Question 12. Part A. So it says calculate, and it's got a list of numbers. And once again, it's checking if you know your BidMass rules. So it says give your answer correct to 2 decimal places. Well, now we're not going to take any risks. We have a calculator, so we're going to use it. Because your calculator will also function in the order of BidMass. So we've got square root, so we've got our square root sign here. What's in there? So 5 times 3.8. Now we're going to go out. So I've just clicked the sideways button there. You can do that on your calculator. So we want to get out from under that square root sign. So then plus 2.1, and we want it squared. So we've got this x squared here. So I'm just going to zoom in a little bit. So there's our square root sign. And then we're going to use this squared sign so it looks like x to the power of 2. I'm just going to click that there. And we get 8.768889 and all of these different numbers. But it says give your answers correct to 2 decimal places. So what we're going to do first is we're just going to copy this out verbatim. You don't have to copy the whole thing, just more than 2 decimal places. So 8.7688. Okay, that should be enough. So now we're going to solve to 2 decimal places. So that means that we want to have this as our last number. So we're going to put a dot, 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 dot here, and we're going to look at this number to the right of the number we want. We could see that's 8. When it's 8, it means we round up. So it would be 8.7, rounding 6 up, that's 7. Part B. Write 0.05834 correct to one significant figure. So significant figures are different to decimal places. Decimal places, you start counting from after that point, after the decimal place. So then you'd have your first decimal place, your second decimal place, which is what we solve for, third, fourth, and so on. But significant figure, all that means is the first number that you counter that's not 0. So in this case, That's that 5. So yes, that 5 is in the second decimal place. We're going to write this correct to one significant figure. That means we're going to round to only come to that second decimal place. So once again, we look to the right of our first significant figure, to the right of our second decimal place. We've got an 8, so we're going to round up. So we've got 0.06. Question 13. So we've got an absolutely huge graph here that takes up the whole of the page. So the actual questions, what it wants us to do, is going to be in the next sheet. But if we go back down to the bottom, we see the x-axis is hours of exercise per week. Scroll back to the top, the y-axis is resting heart rate. And if we do a quick look before we even read anything else, we can see our data points here. So I'll get my laser, our data points here. And we can see that it's trending downwards. So the more hours of exercise someone does a week, the lower their heart rate is. And that makes sense relative to the real world. If you run a lot, you're going to have a low heart rate. So let's scroll back up and read what it says. So Ken measured the resting heart rate in beats per minute, so BPM, of 12 people. So he should have 12 data points at the bottom. He asked them how many hours of exercise they usually completed each week. And the results of 7, so we've not plotted all the points yet. So this shows the importance of reading the question. The results of 7 of the people have been plotted on the scatter diagram. So there's 7 points already plotted here. So now if we go to the next page to see what the question is, it says here are the results of the remaining 5 people. So we've got hours per week, resting heart rate, and we've got some points. So part A, plot these results on the scatter diagram. Okay, well let's just do them one by one. And I'm going to skip to the end and show you what that looks like. So now in red, I've added on the additional points it's asked me to draw for part A. And when I was doing my plotting, I was just writing the hours as my x-axis or my bottom axis and my resting heart rate as my y-axis. Keeping in mind coordinates I've written with x and y. Part B. Ken recorded one person's resting heart rate incorrectly. Circle the point on the scatter diagram that's most likely to be. So let's have a look at our scatter diagram. So what we're looking for is anything that doesn't follow the trend. So it's probably going to ask us to do this for the next part. We've not fully read it yet. But the trend, I'm going to draw this on just for now, it's roughly there. It's going through all of these points and we're going to look for outliers. Well, the one that stands out to me is the one all the way down here because it's nowhere near the line. It's the furthest from the line. It doesn't really follow the trend. So that point there is at about 0.5 hours and they have a resting heart rate of 48. So that's insane. That's like someone who's like an athlete. But they only exercise for 30 minutes in a day. They either have some sort of heart condition that's making their heart rate really low, or it's, as it says here, that Ken's recorded something wrong. So we've done that. We've circled on the scatter diagram where we think that is. So now it says, describe the relationship between hours of exercise per week and resting heart rate of the people Ken asked. It says, ignore the result that was recorded incorrectly. So we go back, well, it's exactly what we said when we first looked at this graph. We can see that as the resting heart rate decreases, that correlates with the number of hours of exercise. Or rather, the more you exercise, the lower your heart rate is. Now this could be called a negative correlation. Negative because it goes down as the other one increases. So now if we go to the question, we're going to write this. It said negative correlation between hours exercising and BPM. You would also have got the mark if you just stated as the number of hours exercising goes up, the BPM goes down. Question 14. Straight away, we can see there's a table. It's going to be some sort of wordy probability question. We're going to pick it apart. We're going to get our marks. So part A, Geomet High School has 740 students. And anytime with these questions where you're given numbers in the words, I'm just going to underline it. Because I don't want to have to read everything again. I just want to be able to see the important information. 240 students. Each student was asked which method of travel listed below was their main method of travel to school. The table below shows the method of travel together with some of their probabilities. Okay, so now that we've read these, we don't need to read that again. We don't need to read that again. We've got a list of probabilities and we've got some missing probabilities here. So it says a student is chosen at random. What is the probability that this student walks to school or travels to school by bus? Well, let's read. So it says probability that they walk or use the bus. So when it's an or question, you're just going to do the probability of walking plus the probability of using the bus. So that is just 0.55. So more than half the students do that. Part II. How many of the 740 students travel to school by bus? Okay, so we've got a probability that's in its decimal form. We know how many students there are. So now what we need to do is just multiply them two numbers together. 740 times our probability of the bus, 0.35. So I can't do that in my head, so I'm getting the calculator. 740 times 0.35. So it's 259 students. III. The probability that a student travels to school by car is twice the probability that a student travels to school by train. Calculate the probability that a student travels to school by train. Okay, so it's given as a relationship between these two currently empty probabilities. Well, the first thing we need to know about probabilities is, so you can even write it down, probability all add to 1. So all of them probabilities added together should equal 1. So that will tell us what the probability of car and train, at least together, would be. Because we know that 1 should equal, so we're going to do the probability of walking plus the probability of using the bus plus the probability of using a bike. Wow, there's a lot of people using a bike in this school. And then other, there's 0% probability. So we're going to put plus, and that's car and train. So we can now write that out. So we're going to add up the values that we already have. So that adds up to 0.85 plus car plus train. So 0.85 plus these two unknowns would equal to 1. So if we take away, we could treat this like algebra. We could take away 0.85, 0.85 from each side. That will give us that the probability of car plus the probability of train is equal to 0.15. Probability that a student travels to school by car is twice the probability that the student travels to school by train. So that means we can say that car is equal to 2 times train, because it says right there the probability is twice the probability of train. So now we can say 0.15 equals 2 times train plus train. So we're just going to simplify that. So that's 3 times the probability of being on the train equals to 0.15. Well, dividing both sides by 3, we know the probability of train then was just 0.05. So now we can slot that in to our table, 0.05, and rather than going back to all the algebra, we already know that the probability of cars twice the amount as the train, so that would be 0.1. Lovely. Part B, we've been given a Venn diagram. We can visually see that, and the words say the Venn diagram shows information about the number of students who study music and drama in year 11 at Geomet High School. So we've got some numbers here. So 17 are studying just music, 11 studying just drama, and 14 are studying both music and drama. That makes sense to me. People who like music tend to like drama. It now says there's 104 students in year 11. Complete the Venn diagram to show the number of students in year 11 who do not study music or drama. Okay, so in total we've got 104. Of them 104, and we're going to start taking away, because 104 is all of the students. And we've been told that 17 study music, 14 study music and drama, and then we've got 11 that study just drama. So that will give us the number of students who don't study music and drama, and don't study drama. And that gives us 62, and you can write that into your diagram there. Part II. What is the probability that a student chosen at random from year 11 studies music? Well, let's make that into a fraction. So we've got 17 students who study music, but it doesn't give any other conditions. It just says studies music. It doesn't say just music, and it doesn't say music but not drama. It says music. So the 17 who study just music, and we're also going to include them 14 who study music and drama. Now we've got them groups, we've got the number who study music. That's out of the total number of students, which is 104. So once again, we're just going to put that into a calculator, so it'll give us the most simple form of that fraction. I've just put it into fraction form there, clicking my fraction button, 17 plus 14 over 104. So I'm just going to write down my fraction, 31 over 104. I've just checked my mark scheme. Just in writing this calculation here on the left, you would get 1 mark. It's the simplification, putting it into your calculator, that gets you that second mark. Question 15. We can see there's a big diagram here with lots of little measurements on. And we can see at the bottom of the diagram it says not drawn to scale, which gives us the loud hint not to use our ruler in this case. So it says a shop sells storage boxes. A stack of 4 of these boxes is shown below. So we can write here there's 4 boxes. The height of a single box is 35.2 centimeters, and we can see that labeled on the diagram. It says the height of 4 of the same boxes when stacked is 52 centimeters. So that's also labeled on the diagram. It says a different stack of these boxes is a height of 85.6 centimeters. So how many boxes are there in this stack? So what we want to do is try and make an equation from all these words and all these measurements so we can figure out the number of boxes. So if we start writing things down, so we'll have, so the total height, so 52 centimeters, is equal to an initial height of this box is 35.2 centimeters plus, and now let's have a look. Well, our initial height goes from the bottom of that box there up to the top. But then each time you add another box, you're just adding the height of this lip here, what we're going to label L. So lip there and a lip there. So when there's 4 boxes, you have that initial height here, and then you add on 1 to 3. So 3 times L. So that 3 in relation to that 4, it's 1 less. So when there's 4 boxes, or when there's n boxes, for example, so it could be any number, it could be 2 boxes, could be 10 boxes. So if we have n boxes, the number of lips that you will get will be n minus 1. So now going back to our equation, the total height there, 52, would be equal to the full height of one box plus n minus 1 times that lip that we don't know right now. We don't know what that lip height is. So now we've got an equation that has 2 unknown variables. We can't solve that. We don't know how to do it. But what we can do is we can try and solve one of the unknown variables, so L, what this lip is, by substituting in values that we do know. So apologies there. So it's not 52 centimeters at the moment. Because this equation's written with our variables, we're just going to call this T. The total height of the boxes would be that initial height, that one box, plus n minus 1, so 1 less than the total number of boxes times that lip. So now we're going to substitute in, and now we will have 52 centimeters, so we're going to do the case of 4 boxes, so 35.2 centimeters plus, so n minus 1, well n in this case is 4 minus 1, so that's just 3, we can write that down straight away, times L. Cool, so now we have an equation where we only have one unknown, that value of L, and we're going to solve for that value of L, because once we know that, we can put it into our original equation, which will mean that we'll be able to solve for n, which is the number of boxes in total when the stack is this high. So we're doing it in steps. And keeping in mind, okay, even if you don't get to this last step here, this final step, you still may get marks trying to figure out this value of L. So to rearrange, we want to get L on its own. So first we're going to take away 35.2, 35.2 from each side. So the equation stays balanced, each side is the same. So that would be equal to 3L. And we're going to get our calculator out. And we're going to do 52 minus 35.2. So that's 16.8. So now we're going to divide by 3, because we just want L on its own. At the moment we've got 3 lots of L. So then L would equal that 16.8 that's already on our calculator divided by 3. So that gives us 5.6 centimeter. So each one of them lips on our diagram is 5.6 centimeters high. And at that point, looking at the mark scheme, we can see that we have got 2 marks. You've already got 2 marks, and you've not even done the bit where you're finding out what this number is. Okay, so now we're going to put that value of L back into our original equation that we made. So the total height would be equal to 35.2 centimeters plus n minus 1 times 5.6 centimeters. So now we can just substitute in again, because we know what the final height is. So 85.6. And what we're trying to solve for now is what the value of n is, how many boxes there are in this case. So that would be equal to 35.2 centimeters plus n minus 1 times 5.6 centimeters. So once again, we're going to start by taking away at 35.2, which will give us, using our calculator, 50.4. Next, we're going to get rid of this times sign. So we're just going to divide by 5.6 centimeters on each side. So that's just equal to 9 centimeters equals to n minus 1. Or rather, when we divided through, we were dividing 50.4 centimeters divided by 5.6 centimeters. So actually there's no centimeters there. The centimeters, when you're dividing through, the units also cancel out. So now we just have 9 equals to n minus 1. Okay, so well, what would n be? We want to still solve for n, we don't have n on its own. So now, all we're going to do is add 1 onto each side. Add 1, add 1. So you'll get 10 equals to n. And that there is the final answer. So you'll have, when you have a height of 84, like it originally told us, so 84.6 centimeters, we substituted into our equation and we found that that is equal to 10. You have 10 boxes stacked. Another way you could do this question, if you're not a big fan of algebra, I'm a big fan of algebra, so I always use it. But another way you could do this question is to go, okay, the total height here in this case is 52 centimeters equals 35.2 centimeters plus, and then it's like 3 times something. 3 times, I don't know what it is, these little lips. So to find what that little lip is, you do all your steps again, so you just minus through your 35.2, divide by your 3, you get your 5.6 centimeters, okay? So you find what your lip is. You do a little bit of algebra, that's okay. But then at this point, you're okay, I don't want to do the algebra rearranging, I found that really difficult. What you could instead do is just 35.2 centimeters, and then just keep adding 5.6 centimeters using your calculator. So once, twice, however many times, until you get your value equal to 85.6 centimeters. At that point, you can just count up. So your first box would give you that amount, and each box after that, so 2, 3, 4, and so on and so forth. You're just going to add the height of the lip, and you can just keep adding and counting until you get to 10 boxes. So that way uses a lot less algebra, and if you're not a fan of it, feel free to do it that way. Question 16. This is a nice little bit of algebra. There's 2 marks to get here. If you don't like algebra, you might straight away go, I'm not going to bother. There's not enough marks for me to waste my time here. But actually, it's quite simple. So it says make G the subject of the formula. And when it says make something the subject, it just wants you to get G on one side of an equation, so with an equal sign there, and then whatever is going to be on this side. So we're going to underline G. So to start off with, we want to get one side to have only terms of G. So that 2G, we want it on its own. So because it's an equation, if we do the same thing to each side, then each side is going to stay equal. So we're going to take away K each side. So that would give us H minus K. And you can't write that any simpler because we don't know what them variables are. You can't simplify them anymore, so you leave it as is, equals to, so you have minus K, you've got a plus K, they would cancel, that would cancel out. So now you just have 2G. So now we want G in its own, and we've got 2G. Well, anytime you want half the amount or just one of the number and you've got 2, you just divide by 2. So now we're going to have H minus K, and that's all divided by 2. Once again, we can't write that any simpler because we don't know what them variables are. They're unknowns, that's as simple as it can go. And that would just be equal to G. Now you may be asking yourself, oh, algebra's really hard. What else is there to do? That's it. You've done 2 steps. You've got 2 marks. Nice and easy. Question 17. We've got a grid. We've got some numbers. And part A says translate this triangle using the vector 3 and -4. So for vectors, you have to remember it kind of looks like coordinates, but it's got numbers at the top and the bottom instead of left to right. That top number is where you move in the x direction, that bottom number is where you move in the y direction. So for each point of this shape, this is a point there, point here, and point here, we're going to translate, i.e., or meaning, we're going to move it +3 in the x direction. So we'll start with the x direction first. So I'll write this in green. So 1, 2, 3. So the new point, and I'll put that in yellow, will be here. And we'll do that for each one. So 1. Okay, so that's if we were just translating in the x direction. But we're also translating in the y direction, and we're going to move -4. So we're going to move 4 down in the y direction. So I'm going to get my green again. So from these yellow points, so we've done our translation in the x direction, we're just going to move down 4 in the y direction. So 1, 2, 3, 4. Once again, we'll mark on in yellow. That shape has been translated. We just need to connect the lines to show where it is. So I've done that in blue. And you can see now visually the shape itself has not changed shape, it's not changed orientation, it's not rotated or anything. It's exactly the same, it's just been moved 3 to the right and 4 down. Now this says rotate the shape 90 degrees clockwise about the point 0, 0. So the point 0, 0, we're going to mark in red. That's just where these axes cross over. So you can even write 0, 0, that's there. And when we're rotating 90 degrees, you could, if you have tracing paper, this is very easy to do. You'll just draw your shape with your tracing paper over the top, put a dot on, and then holding your pencil on that tracing paper, physically rotate your shape 90 degrees. So you're just going to turn it from your paper being one side up, say like this. I'm going to do the other sides in yellow, to being then put that here, being the other way up. So you can see I'm rotating that way around, and keeping in mind it says clockwise as well. So I've taken that for granted there, but clockwise is the same direction as a clock. Imagine your clock, you've got your hands, and that minute hand will rotate to the right, and that's why we're rotating to the right. Okay, so we've got our point, we know what we're doing, we're rotating 90 degrees, we're going clockwise. So now imagine what's going to happen to each one of these points. So as we're rotating, this distance here is going to stay the same. Yeah. So that distance is going to stay the same for each one of these points. Because all it's doing is rotating, it's not moving away from the center. So when that rotates 90 degrees, it will end up, and I'll do this in green, and I can do this by observation because I've done it quite a lot, but if you've got your tracing paper that makes it easier, it'll end up here. And if we double check, yeah, that's 3 diagonal. So 1 across in X, 3 up in Y, away from that point. That's the same distance as it is on that left hand side. Okay, so we've got our first point. Now our second point, that's 4 away. That's 4 away there. Our third point up here. Because now we have these 2 points, and I'm just going to draw in blue with a line. These 2 points are the same as these 2 points, and it's been rotated to the right. This makes it very easy to draw now, because we know that it'll have 2 along here, 1 down, 1 down. So all I'm doing is using them 2 points in the line that I first drew, and then just saying, okay, well, I know that it'll have this shape, this shape, this shape, this would look like this. So if you don't have any tracing paper, you've messed up, you've not brought any in, just take 1 point, rotate it, maybe take a second point, think about where it is relative to the first point, and the rest of the shape you can draw relative to the points that you've already rotated. It makes it a lot easier. Question 18. Now, as someone with a physics background, it fills me with a giddy glee anytime that I see a physics equation in a maths paper. But all physics is, and you may have seen like this old meme, this old joke, physics is just applied maths. It's where you use maths principles, maths techniques for real world problems. Similar to engineering, but physics is more spacey, theoretical. But in this case, we've got pressure equals force over area. So they've given you that formula, you didn't need to remember it. And we've got a diagram of some drawers, office drawers. So it says the base of a filing cabinet is a rectangle. It measures 14 centimeters by 60 centimeters. And as someone with a physics background, I would just draw that straight onto the diagram. So we know it's 60 centimeters by 45 centimeters. It's going to be a rectangle that kind of looks like that. The whole of the base is in contact with the horizontal ground. So all of this is touching the ground. Then you could draw your sides on, so 60 centimeters, 45 centimeters. Part A. The empty filing cabinet exerts a force of 675 newtons. And newtons force, we can see we'd plug that in to the equation here. It says it's exerting that on the ground. What is the pressure exerted on the ground by the empty filing cabinet? And it said gives your answer in newtons per centimeters squared. Okay, well, we've got our equation. We've been given the force, so we can just plug that straight into the equation. So I write the equation out again here. Force over area equals pressure. We're solving for pressure is already in the right format, so we're just going to substitute in. We know 675 newtons is the force, and then the area that's touching, well, it says the whole of the bottom of that cabinet's touching, and it's giving you the lengths of the sides. So the area of a rectangle, it'd just be 60 centimeters times 45 centimeters. And you can just plug that straight into your calculator. You could even keep it in fraction form to keep it nice and easy. 675 over 60 times 45. And you don't need to convert to meters or anything, because it's telling you it's in centimeters squared. You want it in centimeters. So that gives us 0.25. And it says give your answer in newtons per centimeter squared. Part B. When the filing cabinet is full, so absolutely filled with files, the pressure it exerts on the ground is 0.75 newtons per centimeter squared. So this time it's giving you the pressure first. It says, what is the force that the full filing cabinet exerts on the ground? Give your answer in newtons. So let's write out the equation again, and we're going to substitute in. So we've got pressure equals force over area. So substituting in pressure, we've been given it this time, 0.75 newtons per centimeter square. And that's equal to, we want to know what the force is, so I'm just going to leave that as F. It's an unknown variable, I don't know what it is yet. And that's over the area of the bottom of the cabinet. So 60 centimeters times 45 centimeters. So this time, we're going to rearrange. We're going to times that pressure by the area to get our force on its own. So we're going to times by the bottom here. So 60 centimeters times 45 centimeters. And I'm going to times both sides. Times that right side was caused that to cancel out. Timesing that left side will give us what the force is. 0.75 times 45 times 60. So that's 2025. And that is in newtons. Question 19. The diagram shows information about the percentage of households in Eduvale, which just before recording this, I had to try and get my sensible head on, because I'm just imagining Eduvale as like this vast valley of like teachers and schools and like a harmony, and honestly it sounds kind of hellish. We've got to do our maths. Maths is very useful for real life. I do not want to live in a utopian education valley. But anyway, Eduvale, that owned a desktop computer for the even numbered years from 2006 to 2018. So we've got our nice graph and diagram there. On the left hand side it says percentage, and on the bottom it says year. We can see there's kind of like a positive trend, so it's going from low to high, but it's like this big bump here. So now part A, I, says complete this statement. The percentage of households that owned a desktop computer decreased the most between the even numbered years of something and something. So we're looking where the number of people with a desktop decreased the most. Starting at 2006, we've got a steady increase, so it's increasing, and we can see that because the percentage is going up on this left hand side. So it goes up, 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 until we get to here, this nice peak, and then suddenly it drops, and then it drops again. But that second drop is not as big as that first one, and we can tell because it's not as steep. That tells us that it decreases the most between this really high peak and this lower peak here. So that's between 2014 and 2016. So we're just going to plug that into our answer. Part II. Jane says the graph shows that 70% of people owned a desktop computer in 2009 because it passes through that point. Let's just double check that graph. So we can read it a little easier, we're going to draw a nice straight line up from 2009, so that would be right between 2008 2010. And we have a look up, so we're going to go from that line and we're going to draw to here. And yeah, it's thereabouts passing through that 70 at that point. What you've got to keep in mind is every 2 years they took the data, they plotted these points. But in 2009, there's not actually a point there. They've just extrapolated the data. So that means they've got 2 points either side and they've gone, it's probably gone this direction. But we don't actually know that. It might actually be lower, it might be higher. This is just a guess based on data trend. So I would say, no, Jane's not right, because the data is not plotted for 2009. That would get you all the mark. Part B. The table shows information about the percentage of households in Eduvale that had an internet connection for the even numbered of years between 2006 and 2018. So we've got years there and we've got internet connection with a percentage. So it says on the diagram on page 24, plot the information for internet connection. Wow, this paper is very plotting heavy. So if you well, I suppose it's only 1 mark to gain, so it's not all lost, but it would be annoying if this isn't something that you're very good at. So keep in mind, you plot things following the x-axis first and then the y-axis. So your x-axis is your year, 2006, and your y-axis is your internet connection. So I'm just going to skip ahead to where I have plotted these points. Now we've got all our points marked on our graph here in red crosses. We're going to look at the difference between the black points that were already provided to us and the red crosses. So just by observation, I'm going to mark this in green. I can already see these points here, these points here. There's not that much of a difference. So we want to focus on the ones with bigger differences. Well, we can also see that this one to the right, this one here, is bigger than this one. So we know it's not that one. We can also see that this one to the left is bigger. So we know it's not that one. So now we've got 3 left that we just need to double check the size of. So starting with this one on the right, so that's about 17. This one on the left down here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 10 difference. This one over here, so that's 12 difference. So the biggest one is this point over here, which corresponds to the year 2018. So now we can write that down. So there's 17 difference, and that's for the year 2018. Part I. Edgevale is a large town in a county. Comment on how in this county the percentage of households owning a desktop computer and the percentage of households having an internet connection are likely to have changed in this time period. So let's have a think about this question. You've been given data about Edgevale, which is a town, and it's asking, okay, this town has been recorded, but we want to know about the county. So first of all, you could say the trend in the county likely matches Edgevale. So you know that the county and the town, they're likely going to have similar trends. And now we're going to think, okay, well, they're going to have similar trends. We have the data for the town. So looking at just our red crosses, there seems to just be a positive correlation. So it's increasing. It's not increasing as much at this top end, but it's still increasing. Whereas for desktop ownership, shown by this black line, it increased to a point. What year is that? So it peaked in 2014, and then it's going down. So it's asking us to extrapolate, to guess, okay, what's the trend going to be beyond our data set, beyond the years that we have? Well, for the internet, it's increasing, and as far as we can tell, it's just going to keep increasing. So we can put the internet will increase previous, and the desktops were increasing to 2014, but after that they were decreasing. So we can guess desktops decrease. Question 20. We've got a diagram, a circle inside a square, and it says underneath the diagram that is not drawn to scale, so we're not going to use any of our tools like rulers. So it says, part A, the diagram shows a circle inside a square of side 8.2 centimeters, and that's labeled on our diagram there. The side of the square are tangent to the circle. So it says find the area of the shaded region, and you must show all you're working out. So when it says tangents, you might go, oh, that's a word that I don't know. But when something's tangent, so if I draw a circle, it just means that it touches the circle at one point. It doesn't go in the circle, I've done a terrible drawing there, but it touches it at the edge, lies at one point. So it's just letting you know that that circle fully fills that square. That's all it's saying. And you might have glimpsed that from the diagram. You could go, oh, I don't like that word, I'm just going to cross out that bit. I'm just going to look at the diagram, base it on that. That's perfectly fine as well. So now what we need to do, we want to find the shaded area. Well, we know how to find the area of a square. So imagine the circle's not there. We could do the square as just 8.2 centimeters. And because the sides of a square are all the same, just times 8.2 centimeters. So let's plug that into our calculator. That gives 67.25. But then that square is filled with a circle. And we know for a circle that its area is pi r squared. Well, what would r be in this case? So r is the radius. So for a circle, the radius would be from that middle point, a line going to the edge, that distance here. Well, looking at this diagram, we could see that the full diameter, so from the top of the circle to the bottom, the diameter is equal to the square side, so 8.2 centimeters. And if the radius is just from the edge to the middle, that means the radius, so r, is half the diameter. So it'd just be 4.1 centimeters. Cool, so at this point we can just plug it into our equation. So pi times 4.1 squared. So pi in our calculator here, we're going to click shift to get pi. If you don't know how to find it and you're in a panic, it does actually say in the front of this exam that you could just use the number 3.14 instead of pi. But we know where pi is, so pi times 4.1. We're going to use the squared button there to get the little 2 at the top. So we click equals, switch that to decimal, and we do it to 2 decimal points, so to that one. So it's 52.81. Oh, and that's squared up there because it's an area. Okay, so we have the area of the square, we have the area of the circle. We can see the area of the square is bigger. That makes sense. It takes up more space than that circle. And we want to know the parts of the square where the circle isn't. So we're just going to do the square area, so 67.25 centimeters squared, minus our circle area. It's 52.81 centimeters squared. And plug that into your calculator. And that gives us 14.44. And just checking the mark scheme. So if you rounded your number earlier on and you carried forward that rounding, so if you got 14.42 or 14.46, you would still get the mark. Part B. The diagram shows a parallelogram. It is the cross section of a prism. And if you remember back to the start of this paper, we actually had a drawing of a parallelogram and we discussed it briefly, but we'll say it again now. Parallelogram, that means that these sides here are parallel and then the other side here is also parallel. So it says it's the cross section of a prism, and it also says diagram not drawn to scale, so we're not going to use any of our tools. We're going to use what we know about these shapes. So the length of the prism is 16 centimeters. So find the volume of the prism. Okay, well, we should know for a prism, I believe this formula is given at the start, but it's the length times the area of the face. So the face in this case is this parallelogram. So this formula for a prism is true for if it was like a triangle at the front, if it was a hexagon at the front. It's just that area times the length. So now we know how to get the volume. We've got our length, so we just need to find the area of our parallelogram. So let's start breaking the shape apart and thinking about how to find the area of a parallelogram. Well, looking a little closer, it's already given us some things. Before we drew on our diagrams to show these are parallel sides, it's put a dotted line and it's put a right angle. It's showing you what the height is here, and it shows you what the base length is as well. Now I've put that line in straight away on the opposite side to show that what we're essentially going to be doing is finding the area instead of a rectangle that looks something like this. So if I now draw that in green, for example, and I'm doing that by moving this triangle over here, and I'm moving it into this empty space. So now all we need is the base of the rectangle. Now we turn the parallelogram into a rectangle. So that's 9.8 centimeters it's given us here, and we can see that the height is 7 centimeters. So that area is just 9.8 centimeters times 7 centimeters. So that's 68.6 centimeters squared, because that's the area. So now we're just going to do the area times the length. So the length is 16 centimeters times 68.6 centimeters squared. So that's 1097.6. Remembering your units, we get centimeters cubed. In the mark scheme, it says if you rounded at the point of finding your area face, it'd be fine if you also get 1098. Question 21. We can see that it's being nice, the paper, the examiners, they're letting our brains rest from using our calculator. They're giving us some nice, easy algebra to do. So you might even get this sort of question occasionally in your non-calculator paper. So what we're going to do, we're going to do the same thing to each side of this equation until we get just x equals to something. The first thing I'm going to do, I have x's on both sides, and I want to start by getting x on just one side. So we've got 7x on the left, 2x on the right. So I'm going to take away that 2x, because I know if I take away 2x from the left, take away 2x from the right, so I'd get 7x minus 2x minus 5, and I'd get that equal to 3. Okay, well that 7x and that minus 2x, that's going to give us 5x. So minus 5 equals 3. So now we can see we've got x on just one side. That's a lot easier. The reason I took away the 2x from the 7x, I could see the 7x was bigger. So if I take away a smaller number, it's going to stay positive. It's going to make it easier for me. So now I want to just get just this x term on this side. So I'm going to add 5 to get that minus 5 to cancel out. So that would be equal to 3 plus 5, that's 8. Minus 5 plus 5, that cancels out, 5x. So then now we want x on its own, so we're going to divide by 5. So at the moment we've got 5 lots of x. So that just gives us 8 over 5x. And looking at the mark scheme, you can just leave it as 8 over 5. Part B. Rosa is buying bananas and apples. Okay, before we even read this any further, we've just done an algebra question. The question's also going to involve algebra. The examiner's trying to lead you into tackling this question with an algebra mindset. So it says she buys X bananas, which cost 30 pence each. She buys 2 more apples than the number of bananas she buys. Her apples cost 25 pence each, and she pays a total of £5.45. Use algebraic method to figure it out. So first of all, there's like loads of information. So anywhere that we don't want to, or we don't need to read it again, we're just going to get rid of. So Rosa's buying bananas and apples, we don't need to read that again. We know that she's paying, okay, in total, it's going to be £5.45. So I'm going to start with that. I'm going to put £5.45 here. That's going to be equal to, so I can get rid of that now, don't need to read it again. She's buying X bananas, so X number of bananas, and that's times how much the bananas cost, so that's 30p. Plus, how many apples is she going to get? She buys 2 more apples than the number of bananas she buys. So we bought X bananas, and she's buying plus 2 apples, and that would be times the cost of the apple. So that is 25 pence. And I've put that there in brackets, so I know that it's the number of bananas plus 2. And we're going to do that calculation first before we times it by 25p. We want the 2 and the x times by 25p. So now we've got a nice algebra equation. Well, first of all, let's simplify. We don't want them brackets in. I put them brackets in so I know that I'm going to multiply it correctly, but we don't want them brackets. And also, this isn't written in algebraic form, because if you had 30 lots of x, or 30 times x, or we have x times 30, we'd actually write it as 30x. We wouldn't bother putting that times. So let's do plus, and now we're going to expand out our bracket. So first we're going to have x times 25, so 25px, and then we're going to have 2 times 25, it's going to be plus 50p, equals to our £5.45. Okay, this is looking very familiar. Well, now we can gather these x's together. We've got 30p times x, we've got 25 times x. So that's the same as 55 times x. I'm just putting that p there to remind me that that's in pence. 55 times pence. And plus 50p. Now at this point, we could convert all of these pences, so 55p, 50p, into pounds. But because I've only got one number that's in pounds, the other 2 are in pence, I'm actually going to convert the pounds instead to pence. So this time I'm going to write this as 545 pence. So we know there's 100 pence in a pound. Okay, this is looking nice and easy now. So we just want to get just x on one side. So let's get rid of the 50p. We're going to take away 50p from both sides to keep it equal. So this would be £4.95 on 495 pennies equals to 55 pence times x. So now this is the final step. We're going to divide through. We just want x on its own. At the moment we've got 55 times x. So we're going to divide through that 55p on both sides. So you'll get x equal to, and I can't do 495 divided by 55, so out comes my good friend the calculator, equals exactly 9. So that means that Rosa bought 9 bananas. We remember that x is the number of bananas. She's bought 9 bananas. That was 4 marks. She did a 4-mark question. For part C, it's giving you a 2-mark question. So you've used a lot of brain power. It's like, okay, we're going to cool down from algebra. We're going to do a nice, easy one. And we're going to factorize a quadratic term. And for this, we know it's going to end up, when we're factorizing it, we're putting it back into the brackets. And it's going to look something like this. X, X. And we're going to have a number here and a number here. We need to figure out what it is. Well, you should know that the rule for this is this number here and this number here should times to make the last number, or sometimes it's referred to C in the general equation. So in the general form it looks like this, bx plus c. So these two numbers are going to times to make 4, but they're also going to add them same two numbers to make 5. Now you could do it as a little riddle like that and say, what 2 numbers times to make 4 and add to make 5? If you're not very good at them sort of riddles, what you can do is you can factorize 4. So you can say, okay, what makes up 4? You could have 1 and 4, 2 and 2. So it can only be a combination of either 1 and 4 and 2 and 2, like one of these factor pairs. You're like, okay, well, I've got all the possible combinations it could be. If I add them to 1 and 4, what does that equal? 5. What does that equal? 4. So now we've added up the factor pairs and we'll go, okay, well, 5, yeah, that's right. That's equal to what B is. We look back, that's 5. We're happy. So that means that 1 and 4, these factors, are what's going to go in here. So a positive 1 and a positive 4. Question 22. We've got a plane coming into land on a runway. We've got a distance here of 2.5 kilometers. We've got an angle listed here, 3 degrees. We see that this looks like a right angle triangle. And it basically repeats all that information in the text below. So we can now just ignore that. All of this is shown in our diagram. So it says calculate the vertical height of the aircraft. So that would be here. I'm going to label that V for now because it's the vertical height. Now the trick for this one is you've got one distance here and you've got an angle here, but you don't know the angle inside the triangle. So this is trying to lead you into using trigonometry, or more specifically the SOHCAHTOA. So I'm putting in these lines here. So the first one would be sine equals opposite over hypotenuse. Second is cos. So that's the sine of the angle, sorry. And then cos of the angle equals adjacent over hypotenuse, and that would be tan equals the opposite over the adjacent. So now let's label on where these opposite, adjacent hypotenuse are. Well, the hypotenuse is easy. That's just the really long side. But then the opposite and the adjacent, well, we don't know what the opposite is until we've got our angle. And if we look at our diagram, we haven't got an angle yet, but we do have an angle up here. We can see that's horizontal. So that tells us that this angle in total, so from this vertical edge up to that horizontal line there, that's 90 degrees. Which means if this angle here at the top from the hypotenuse to the parallel to the horizontal is 3 degrees, that means inside here must be 87 degrees. So this angle, I'll do that in green actually to make it easier. This angle here is 87. Okay, so now we have an angle, which means we can label our opposite side. So opposite to the angle is this side here, the 2.5 kilometers. And adjacent to our angle is our V. So looking, we want to find our adjacent. We've got our opposite. So adjacent and opposite, that means that we're going to use tan, this end one here. So we're going to do the calculation of tan of the angle, which is 87, equals to the opposite, which is what we have, 2.5 kilometers, over, and then what we labeled initially as V. Move that across. So that calculation there, we are just going to plug into our calculator once we arrange for V. So we move back down to where we can do our writing. To get V, we're just going to multiply each side of that equation by V. So I'll rewrite it out again here. So tan 87 equals 2.5 kilometers over V. So we're going to times both sides by V, so we'll get V tan 87 equals 2.5 kilometers. And then we're going to divide by tan 87 because we want V on its own. So we've times by V first because we don't want V on the bottom. And now we're going to divide by tan 87 to get V on its own. So now we'll have V equals to 2.5 kilometers divided by tan 87 degrees. So if we get out our calculator, because I can't do that in my head, so just so I can make sure I've done this correct, I'm going to use the fraction symbol, same as if you just used the divide sign. I'm going to leave it in terms of kilometers, so 2.5, and I'm going to put that over, click the tan button, and that is 87 degrees. Now this calculator, you can see at the top there. Oh, can you see at the top? Let's make this a little bit bigger. You see at the top there is in degrees mode. There's like a tiny little D. So that gives us 0.131 and loads of other numbers. So we're going to put in 0.131 kilometers. Question 23. Now this is the last question of the paper. You can see that they're finishing strong here. There is 6 marks that you can gain doing this question. So it's always worth giving it a go. There's 6 marks to get. You might get some of them, you might get all of them. Always give it a try. So it says Heath has £3,000 to invest for 5 years. So at the start, Heath has £3,000. We'll underline that so we can refer back to it. No extra money will be paid in or withdrawn during that 5 years. So it sounds like, okay, he's got his bank account and he's straight away put in his £3,000. So it says he can either put it in, he's going to choose one of these accounts. Either account A, which is a 4% compound interest per year. Interest rates can vary. So compound interest, it means each year is going to add 4% plus 4%. So if he's got 3,000 in 1 year, after 1 year, he'll get 4% of 3,000 added on. And then the year after, he'll get 4% of 3,000 plus the 4% added on, and so on and so forth. But that, it says interest rates can vary. So that interest rate might go down, it might go up. And then it says account B, guaranteed interest rate at the end of 5 years of £190 for each £1,000 invested. Okay. So it says which accounts gives Heath the greatest percentage increase in his money at the end of 5 years, and by how much is it greater? Show how you decide, state any assumptions that you make. Well, let's start with account A. Account A, nice and easy. Put A. We've already described how account A is going to work. We're going to, so after the first year, we're going to add 4%. Now a cheeky little trick to do this in one step, nice and easy. So you do 3,000 and you just times it by 1. So when you times it by 1, that's the same as having 100%, 0.04. Now that is doing multiple steps at once. So normally you'd divide by 100 and then times by 4 and then add that on top. But what that's doing is all of it in one go. So it's putting it to 104% of what it was before. That's what the interest would be. So you could do this for 1 year and then 2 years and then 3 years. And each time you're going to times the result. So I'll put R for the result. So for 2 years, you would do the result times 1.04 and so on. But that's tedious. We don't want to do that. We don't want to do more work than we need to do. We know that we're going to do 3,000 and then we're going to do 1, 2, 3, 4. So it's at the end 5 years. Yep, so 5. So we're going to times it by 1.04 5 times. So you could write 1.04 to the power of 5. And that's just the same as doing 1.04 times 1.04 times 1.04 times 1.04 times 1.04. But we're lazy. We don't want to write that. So we're just going to put 3,000 times 1.04 to the power of 5. I can't do that in my head. So I'm going to whip out my calculator. And you'll see straight away the first assumption I've made. Though account A says the interest rate is variable, I don't know what it's going to vary to, so I'm just going to assume that it's going to stay around 4%. I don't actually know. So 3,000 times 1.04. And then when you're doing a power that's not 2 or 3, because 2 and 3 have their own buttons here, you see my little cursor moving. To the right is X with a box in the top right. And if you click that, it lets you put in whatever number you want to put in as your power. So we're doing the power of 5. So we get 3,649.9. And because we're doing it in pence, this is a monetary amount. It'll only go to the second decimal place. So we'll round. So 3,649 and 96 pence. So we know how much we've saved here. So now let's do account B. Okay, well we've got £3,000, so we've got 3 times £1,000, which means we would get an additional 3 times £190. So that is, we'll plug that into our calculator, 3 times 190, so £570 on top. So if we add that onto our original amount, so that would be £3,570. Nice easy calculation there. So we've worked out how much we'd get for B, we've worked out how much we'd get for A. So now we can visually see that account A gives the greatest interest. It's 650-ish quid, the other one's 570. But now we need to do some extra work. So we want to know the percentage difference increase of A and B. So we can do that. 3,000 is what we started with. That's 100%. And we want to know the percentage difference between these two. Well, what's the difference? What's just the difference? Well, we could take them away from each other. 649.96 pounds. Take away 3,570 pounds. And now dividing by 3,000 and then timesing by 100, because remember it's a percentage. So dividing by 3,000, that would just give us the decimal or the fraction. We want percentage. We've timesed. This will give us the percentage difference. So we get our calculator, because we can't do that in our heads. I'm going to use the fraction one here, just so I can visually see that it's the same as what I've written down. 649.96 minus 3,570 over 3,000. And we're timesing that by 100. So we'll say 2.7. So I'm rounding that 6 next to the first decimal place up. So we'll have 2.7%. So I can go back to my question now and write that in the box. So 2.7%. And that seems about right. Like they're quite similar, but one's definitely bigger. And now we can write down the assumption that account A interest stays the same. And that has given us all the marks. So if you just made that assumption and wrote that down, you get 1 mark there. The final answer gives you 1 mark. That calculation of the percentage and stating A gives you 1 mark. And then all that working out, there's actually 4 marks worth of stuff in there for you to earn. So even if you don't get to the end, there's still loads of marks to gain. Now we're on to the part B. Comment on the effect that your assumption in part A has had on your decision. Well, we can say that, like we said at the beginning, that interest rate might go up to 6%, and that'd be happy days, lovely, it's gone up, we're getting more money, yes. Or it could have gone down, and actually we got a worse deal. I've had an account that was a savings account, and at one point it went down to 0% interest, so I was losing money when you consider inflation. It wasn't great, and that's not happy days. So you could say the interest might have gone up or down, so final amount in account A may have been more or less. And that is the end of that paper. So once again, this has been John with Page Tutoring. If you like the videos that I'm doing, feel free to like and subscribe. I hope that you're finding them helpful in your revision for the upcoming exams.